I'm Jim Harter. I thought I'd take a little moment to review the crack growth rate models that are available in AFGROW. There's been some questions from time to time about what the different models are, what the strengths and weaknesses of the model, so I thought this would be a good opportunity for me to go over all this. And so what I'd like to start out with, a very short overview of AFGROW, and then get into all the details of all of the crack growth rate models that are available. So first, I wanted to make sure everybody understands that AFGROW is an analysis framework. It's a very flexible and user-friendly tool. But because of that, there's a lot of options. And so we have several different crack growth rate models. And we wanted to use a code like AFGROW because we want it to be a flexible tool that anybody can use and tailor it to what individual needs might be. And AFGROW currently is used in the aerospace industry, it's used in the automotive industry, civil engineering, pipeline industry. So AFGROW is being used in a lot of different places throughout the world right now. So talking about crack growth rate, one of the things that really the reason AFGROW exists is because at the time I started, the crack growth codes that were available didn't have any good way for anybody to validate a model. So you would choose a model and you would just say, well, that's my model, that's what I'm going to use, and you would never be able to compare it to actual raw data. So the big issue for me with AFGROW was to always plot your model so you can see it. And then even better, if you could then paste raw data on top of your model, that would give you a way to validate your model. So that was a really important issue. And I think people who use AFGROW, who have used it for a long time, have probably taken advantage of that. But this is a way for you to say, look, whatever model I'm using, how well does it compare to test data? All right, so let's get into each one of these models. The Foreman crack growth model is probably, I'd say, the simplest model in AFGROW. It's just an extension of the Paris law, and you can see there the denominator has a way of shifting the curves as a function of stress ratio. But the thing about the Foreman model is the shifting is assumed to be uniform. There's no way to adjust it. In addition, it does give you some ability to look at what happens at the high end. So you're asymptotically going to failure as your delta K approaches the critical K. But there's no way to change the amount of shifting as you, say, get closer and closer to an upper or lower limit. So it won't capture the behavior on the low end, the threshold behavior. Although in AFGROW, I'll show here in a second, we could use up to 3 segments to try to model the sigmoidal shape of the curve. So the implementation in AFGROW allows you again to use up to these 4 segments, and these different sets, as we call them, we have 3 different sets you can use. You could have them cover different stress ratio ranges to allow you to fit actually raw data better, but it's a little bit more complicated. In addition to that, we can do mapping. So you could map the stress ratio over a certain range to be set equal to a different stress ratio to allow you to limit how much the shifting goes on. But of course, if you just want to use the Foreman equation as intended, you would just use one set and then leave everything else in AFGROW blank. Okay, the Walker equation it's just a modification to the Paris law, but in this case, what you have is 1 minus r raised to the power m minus 1. Now, some books you'll see that exponent is just a single variable, like whatever, q, whatever they use. I like to use the m minus 1, and that's how it was, I think, originally done. I believe it was, but it makes it a lot easier to understand that the limits for m are 0 and 1. So, for example, if m equals 0, then you can see the equation reduces to d8n equals c times k max raised to the n power. And that gives you the maximum amount of shifting that you could have. So when m is equal to 1, you end up getting d8n equals c delta k to the n, which is again just the Paris equation. But it's also the situation with when there's no effective r. So when m is 1, then you have no shifting as a function of r. And as I said earlier, when m is 0, you're going to get the maximum shifting for r. So those are clearly the two limits. So this is a lot better because it allows you then to adjust the shift to match raw data. And the weakness of the Foreman equation was that you had to play different games to map R and so forth. This gives you a lot more ability to actually match raw data. It still has some disadvantages, but in the implementation in AFGROW, we can have here up to 5 sets instead of just 3. For the Walker equation, since there's no way to capture the asymptotic behavior as we approach failure, then allowing 2 more sets gives you the ability to break it into up to 5. In this case, you see 3 different sets to kind of show the upper end, the mid-range, or the region 2, and then region 1 towards threshold. So you could do that, and in each one of those sets then could use a different m value, so that you could, which is you see a lot of times in the data, you'll see that there's a certain amount of shifting that happens in region 2. There might be more shifting. Well, there is going to be more shifting in region 3. It's just by the way things are, it has to be. And threshold, sometimes you might see more, but it gives you the ability to adjust that. All right, so here's some advantages and disadvantages. As I mentioned, we have more accuracy available because of the ability to change the m. It's simple. It's a closed form equation. Now, the data is really not provided in AFGROW. This is something you'd have to do yourself. And it's going to be difficult to fit stress ratio effects at the limits. And by limits, I mean what I call R low and R high. So as we increase R, at some point, the data will stop shifting because at some point the crack will always be open over the whole cycle. When that happens, you would expect to see the data stop shifting. So that was what I call R high. So when you get close to R high, then this is not going to work well. And then what I call R low is when I go into a negative stress ratio and we plot K max, then we're going to have the same issue because it's going to try to continue to shift. So those are some weaknesses of this model. Now, my tabular method takes advantage of the Walker equation. If you would look at a plot of d8n versus delta k, and you look at different crack growth rates, and you would say at any given crack growth rate, I could then write the Walker equation for 2 different stress ratios. I could have an equation for curve 1 and an equation for curve 2. And since we're using the same rate, I can set the 2 equal. And then the C cancels, the N cancels, and you're left with delta K for curve 1 times 1 minus R1 raised to the m minus 1 power must be equal to delta K for curve 2 times 1 minus R2 to the m minus 1 power. And since we know if we have data and a fit for those 2 curves, we could then, at each crack growth rate, we could then calculate the m. So that would allow us to have a m that would change as a function of growth rate, which would allow us then to more accurately fit actual real data. And it would allow us to also use the same equation to interpolate between those 2 different stress ratios to determine what the crack growth rate curve would be expected to be for some other stress ratio other than the 2 that we fit. And again, since we already talked about this, the m value has to be between 0 and 1. Again, that controls the amount of shifting. So when m is small, or as m goes to 0, the shift is large. And when m goes to 1, there is no shifting. So again, you can see those are clear limits. Now, when we look at what happens when we try to solve for m, Then we need to look at what happens when we have the two different stress ratios. If both of them are positive, we can solve for M as shown here. The next line, if say curve 1 is negative and curve 2 is positive, well then we change the equation. Instead of using delta K, we're going to use K max. Instead of using the exponent M minus 1, we have to use the exponent 1 minus M. Because again, the trend has to be maintained when M is small, the shift is large. When M is large, the shift is small. So that's how you would calculate the M if you had two different, a positive and a negative stress ratio. Now, if we had two negative stress ratios, then we would solve, as you see, the bottom line there. And both cases would be using K max, and we would invert the exponent in both cases. Now, in the implementation in AFGROW, we end up reducing these fits to one stress ratio. So we use the equation that we talked about earlier to then we could, with using the M, we could calculate the value of delta K when R equals 0. And then it makes things simpler because now when R is 0, the equation, it just becomes, there's 1 less 1 minus R in the equation. It's even faster. And it allows me to condense this, this matrix that we use. So each material has 25 different crack growth rates. It has 25 delta Ks at R equals 0 and 25 M values at each one of the growth rates. And then we have my definition of R low, definition of R high, definition of the plane strain toughness, and the material yield strength. So that's how that's implemented in AFGROW. So we have a few materials you can see here. These are example fits. These were never intended to be production. These were intended to give users a way to understand how it works. And if you wanted to, say, look at some typical aluminum or some typical titanium or steel, you could use it to get some ballpark numbers. But these were never intended to be, this was done back in the 1980s. Not that I'm saying that that wouldn't be correct, it's just that I prefer using data that is more current. There's been some changes probably in formulation of different alloys. I would feel more comfortable if I was using this for production work if you had some data and you could use the idea and fit it yourself. But they're there for you. You can see them as examples, so if you wanted to add to that database, you could. Now, here's where we have a lot more accuracy, at least for the interpolation between the two different stress ratios. It allows us to actually model what the data is showing us. And then we have also can say that that Walker relationship allows us to do a better job of interpolating any stress ratio between the two stress ratios that we have fit. Now, it's pretty efficient because we have a very really small table, 25 values of rate, 2 values of R. We're doing a log-log interpolation on each curve, and then we're doing a Walker equation to give us the whatever curve for whatever stress ratio we're interested in. Now, if we extrapolate, one of the disadvantages when you extrapolate beyond the range of the R's that you fit, then you can run into problems because as you approach the limit, the shifting will slow down, and using the M values you had between the two R's will overshoot. So as I get closer and closer to the limit, you should see the trend of the M values getting larger. If we're using smaller M values to extrapolate, we're going to then predict a more of a shift than we would actually see in reality. So that's one of the weaknesses of using just the two curves. And of course, since we only have a handful of materials that were fit as examples, it's going to be a matter of finding the data if you wanted to use it. All right, let's go into the NASGRO equation. The NASGRO equation that we use in AFGROW is from version 3 of NASGRO. That was the last publicly available version of NASGRO. So all of these parameter fits that they have were available to the public. So we were able to implement them in AFGROW. But you can see the complexity here. You also can still see we have Paris law, we have C, delta K to the M, but we have additional parameters. 1 minus the function f, and then 1 minus r, of course. And then we have some additional parameters and exponents that were put in to try to fit curve shapes. And so it's kind of a difficult issue because we have a sigmoidal curve shape, and we also have the shifting that seems to be different at different rates. So this was an attempt to have a closed form equation to try to capture that. But you can see here that means we have a lot more parameters to fit, which would mean to calculate these parameters we would need a lot of data. So and data is not what we don't have a lot of data usually. And so what the NASA had done is they had tried to use the data they had available, make the best fit they could, and then they came out and published this parameter database. And it's there's a lot of materials in the database, so it's very popular. But if you look into it a little more deeply, you'll probably see that when we match this to actual raw data, it comes up a little short, and I'm going to show here shortly. But in the implementation, you can see the parameters, material properties and parameters. You can see the form and shape of the equation, and you can see how we have the shifting at the upper end to be more than you see in region 2, and then they show here in region 1 also a little bit more shifting. That's just based on the data that they had. But unfortunately, a lot of times you'll see data doesn't always behave exactly like this. So they're trying to use a closed form equation to capture the trends in raw data, and it doesn't always work. But they have a large database. So they have a database that you can search, and we implemented this in AFGROW with a search engine. You can find up to, I think it's almost 400 different materials. Again, these are parameters. They have not provided real references for the data, and I'm going to talk about that in a little bit, but it's convenient, and that's a big strength. But here's a situation where if you look at an example fit, here is a comparison for 7178 T6. These data were generated at the U.S. Air Force Academy, and you can see what happens. The fit has a problem when we look at the lower end. As we start to go towards the threshold, a lot of times, or most of the time, aluminum tested in standard air will show this little bit of an inflection point. And because this is a log-log scale here in data in delta K, the difference between their fit and the data in this area can be very large, can be a factor of, say, 3 or more. So depending on where you are on the curve, there could be a lot of difference between what you're going to predict and what actually happens. Now, in region 2, it seems you can definitely see that they're doing a reasonable job. And they also look like they're doing a reasonable job at threshold in this case. But again, we have a gap there where we have the inflection point, and that's been a concern for me. But that's another reason why I like to be able to plot raw data against a model so you can actually look at it. So again, the biggest advantage here is a large database with nearly 400 materials that they have parameters for. And it's sufficient because it's a closed form equation. But as I said, there's curve shape issues, and whether or not that equation will actually match the shape of the curves that exist when you do a overlay. If you overlay the raw data, as I showed you, you can see it might come up short in certain areas. And now, all the data that we have in our AFMAT database includes all of the data that was used in NASGRO version 3, and plus a lot of other data that we've collected over the years. And as I've went through all those data, you can see that we have found data for approximately 100 materials that had data for at least 2 stress ratios over a wide range of growth rate, which allowed us to do a tabular fit. But there's a lot of materials that had maybe data for only 1 stress ratio, and frankly, a lot of materials with no data. So if you do a little digging, you'll see that with nearly 400 parameter fits, they're not backed up by nearly 400 sets of data. So they're widely accepted, but honestly, they aren't, at least for version 3, there's not a lot of data to be able to validate it. So now I'll go to the tabular approach. The tabular approach, to me, is the gold standard because if I have more than data for more than 2 stress ratios, I can take advantage of that. I could use up to 10 stress ratios in our tabular lookup method, which allows us to more accurately interpolate between any 2 pairs of stress ratios using that same method that we talked about earlier with my T method. But the way this works, though, we have one column of correct growth rate, just like we did in my T method, but now we have a column of delta K when R is greater than or equal to 0, or we have a column of K max when R is less than 0. And we have to remember that we always go from left to right, from lowest to highest R. So that we have, again, we have a primary index, which will be our growth rate. Our secondary index is going to be our delta K or our K max. And then in addition to that, AFGROW will allow us to look at temperature or environmental effects. We can have different data sets for different environments or different temperatures. So in your spectrum, you could tag for different environment or different temperature, and then it would know which one of the tabular data sets to use to get your growth rate. So there's a lot of advantages to using the table lookup here. The implementation's straightforward. You can see that you open up the window, you can go to a database, I'll show it shortly, but you can see we've got our column of rates and we've got our columns of delta Ks or K maxes, and again, from low to high, left to right in terms of R, and then our material properties. Now, we also have a database, and this has approximately 100 materials. As I mentioned earlier, in the database, we found 100 materials that had sufficient data to allow us to make curve fits with at least 2 stress ratios and data covering a wide enough range that we could make a decent fit. A lot of times most of the time, we still have to use engineering judgment to estimate the threshold or estimate toughness. But as we get more data, we can always go back in and make revisions. But this is why, in this case, we have 100 materials. In the NASGRO database, they have nearly 400. But don't be confused. The idea is that for all these materials in our table lookup, we can reference them. We could give you, you could go back, look at the raw data. You can actually see where the data came from. So if anybody would ask the question, what's the reference, you can always get it. With the NASGRO equation, you really can't do that. So they're relying on the fact that this is the NASGRO database. But honestly, if you were to dig a little deeper, as I said, you're going to find out that for a lot of material, there's not much to back it up. So here's the same comparison with the table lookup for 71, 78, and you can see that where that inflection point is, because we're using tabular lookup for these different stress ratios, we're able to track that and don't have that same kind of error, say, in that region that we would have had using that closed form equation. So that was the big takeaway here to understand. Now, it's extremely accurate. Of course, the more stress ratios you have, the better it's going to be. We're using a direct table lookup, so we can have the experimental data directly. We can fit the data directly. Now we have to be careful when we extrapolate always, but if we have more than 2 R's, we can use them. So that works to our advantage when we have it. And nothing's better than the quality of the data that we use, so that's another issue. But we always will provide the user with the references that were used for the fit. So you can always go back and check the references and then see for yourself. So in summary, I think the most important thing that I want to get across is the models and AFGROW itself allows you to validate whatever model you're going to use. You can always overlay raw data. and say, does my model really fit those data? That's important. Now, we have a database. So I know a lot of users said it's too complicated to do these fits. So we were trying to make it easy. We've got, again, about 100 materials. So when you look at the T method, we have a small example database. We have NASGRO has their database, and now we have that Tabular Lookup database. So those are available to you. Then if we wanted to look at what you use, you can completely control. So if you think for your case the Foreman's better, you can use the Foreman equation. If you think the Walker's better, whatever you want to use, I always recommend Tabular Lookup, but it all depends on, you might find that we don't have a material in Table Lookup that you want. You might decide, well, I'll use the NASGRO version 3. Just be aware there could be issues with it, but that's all I'll say about it. One of the strengths we have is because we have these diverse models, it gives you the flexibility that you need. And this hopefully will help you to make better decisions when you're trying to come up with inspection intervals or lifing apart. We'd like to give you as much flexibility and options as we can. So that's about it. I hope this helps. So I guess there's some questions. I will go ahead and take a few questions, and hopefully this will help too. Well, that would depend obviously on how much different they are, right? So normally I would expect to see as much as up to at least a factor of 2 scatter in actual data. If I was looking at one data source to another, it's not unbelievable that you would have a factor of 2 difference. Mm-hmm. Now, a factor of 2 difference in rate, now if you were spending your time, say, in region 2, mm-hmm. where we think the curve is fairly straight and log-log scale, let's say the slope was 3. So if I looked at my difference in my stress value, right, I could see cube that to difference in your life. But in terms of just the fit itself, you might see a factor of 2. Mm-hmm. That kind of goes back to why we divide things by 2. We have scatter in the data, and we have unknowns in the load, and so we hope we're not off by a factor of 2 in the data. So we're trying to kind of mitigate all of that. So that's why another reason why I like to plot raw data against our model, so you can visually see if you know how close you are. That makes sense.
Yeah.
Yeah, that happens a lot, and when that happens, I will always tell people if I have one alloy and I have a different temper, let's say, and I don't have data for that temper or that orientation, I would look for a similar material. So if it was a 7000 series aluminum, I would look for another similar 7000 series aluminum and a similar temper. That's about all I could think to do, other than if you can find data, obviously, and try to fit it or compare or at least overlay it, then you can say, does that make sense? But a lot of times, and that's what they did, frankly, in NASGRO version 3, since they didn't have data, they had to do that. They had to say, well, what's a similar material? What are the parameters for a similar material? So that would be no different here. I would just look for the most similar material I could find. Right. Well, you could make your own fit based on any one of those 5 different models. Then you could simply something like Excel, plot the equation, compare, make changes to make it fit. I have publications on the AFGROW webpage. If you go to Documents, there is a publication on, for example, how the Tabular Lookup method works. And it kind of gives a history similar to what I talked about here, but a little bit more detail. And it goes through examples of how you fit. And also our training classes, I always have a section on curve fitting. So we spend a lot of time in training doing example curve fits for Table Lookup.